Now we're ready for problem of 11 from this test review homework. And you can see here the print might be very small, but since it is a story problem, I wanted to put it here so I can just read it. You should have the problem yourself, and then I will explain how to solve it. Let me say a word about story problems. I know most of you don't like story problems, I understand that, and they can be hard at first. Story problems are sort of like exercising. At first it may be difficult and it's hard and you're sore, but then the more you do it, the easier it gets and you're not as sore, and then pretty soon you get pretty good at it. So story problems can be hard. Typically, if you do them enough, you start to see some trends where certain story problems, there's a certain way to solve them, and you get to the point where you read a story problem and then sort of right away you pretty much know how to solve it. So this is an example. This is one example I call a work story problem, because it's the idea that, in this case, I'll just read it and I'll explain. Trent can deliver his newspapers in 10 minutes. It takes Lois 40 minutes to do the same route. How long would it take them to deliver the newspapers if they work together? I call this a work story problem because a lot of times these kinds of problems involve doing a job or doing some task. And that's what this one is. So you've got Trent. He can deliver the newspapers in 10 minutes by himself. Now, Lois, maybe a friend or a sister, if she does the exact same route, it takes her 40 minutes. For whatever reason, it takes her longer. But then the question is, hey, how long would it take them if they work together? So this is a very typical kind of story problem. So what I'm going to do is I'm going to tell you how to solve this kind of story problem. There's a specific kind of equation you use to solve this kind of story problem. Now this equation won't apply to other kinds of story problems. But for these work story problems, what I call work, where one person takes a certain amount of time, a second person does the same job in a certain amount of time, and then ask how long if they work together. Or sometimes they'll say the first person takes a certain amount of time. When they work together, it takes this amount of time. How long would it take the second person by themselves? These are what I call work story problems. So let's go ahead and I'll show you the equation that I came up with. It just works every time. It's actually a very simple equation. So I'm going to say this is for what I call work story problems. Here's what you do. You write a fraction, 1 over T1. T1, the time for first person so T1 is going to be the time it takes the first person to do the job by themselves. Now I'm going to say plus 1 over T2, T sub 2, the little 2 here. That's the time for the second person to do the same job by themselves. All right? So it turns out my equation says that's going to equal 1 over T sub T, where this is the time when working together. So this T sub T is like the together time, right? And that's what these problems are like. They usually give you the time of the first person to do the job by themselves, and then they'll give you the time of the second person to do the job by themselves, and they ask you for the time to do the job if they work together. Those are the 3 times. Although sometimes they may give you the time for the first person to do the job by themselves. Maybe they'll give you the job, the time it takes them to work together, and then they ask you to find the time for the second person by themselves. Either way, it's all pretty straightforward. So for our problem, Trent, it says, can do it in 10 minutes. We'll call Trent the first person. So we do 1 over 10 minutes. Plus the second person, we're going to call Lois. And Lois, it said it takes her 40 minutes. So 1 over 40 minutes. And that's going to equal the time it would take them if they worked together. So I'm actually, for this problem, here's what they're asking me for. How much time would it take them to work together? So I simply have to solve this problem. So let me write it here. Let me leave out the units just so I won't be as messy. Basically 1 over 10 plus 1 over 40. And just to keep it simple, instead of t sub t, I'll just call it t for now. So basically I'm trying to solve this equation here. Now, some of you, since I have fractions here, you might want to find a common denominator and multiply these fractions, and that's fine. One trick that I've learned in math, which I like to do a lot, maybe you don't know this or you haven't learned it. Most of us do not like to try and solve math problems with fractions. It just makes things messy. So here's one little trick that is very useful. Something a lot of us like to do. We like to, what we say, clear fractions, which means get rid of fractions. And a lot of us do it because it's pretty simple. All you do is you have to find the LCD. So you look at whatever denominators you have in your equation, and you have to find the LCD between all those denominators, and then you multiply both sides by the LCD. So that's what I'm going to do here. I have 3 denominators, 10, 40, and t. The LCD for these 3 denominators, first of all, 10 and 40, which are 2 numbers, what's the common number that both 10 and 40 will go into? Well, obviously 40. And then I have the variable t, which I have to add on to it. So the LCD is 40t. Now what am I going to do? I'm actually going to multiply both sides of this equation by this LCD, which is 40t. So what's 40t times 1/10? Well, 10 over 40 reduces down to 4t. What's 40t times 1 over 40? Well, the 40's cancel out. I'm just left with t. Equals, what's 40t times 1 over t? Well, the t's cancel out. I'm left with 40. All right, that to me is going to be a lot easier to solve than a bunch of fractions. 5t equals 40. Solve for t, divide both sides by 5. So this looks like t is 8 minutes. What is t? T is the time it takes them to do the job when they work together. All right, as story problems go, these are actually one of the easier ones, and that's because this equation always works, and it's the one you can use. So you just got to remember this equation, plug in the information they give you, and you're able to solve the story problem. Now when I look at the next few problems, actually I'm not going to spend a lot of time on these. They're actually either easy or I don't think they're that important. Number 12. What is the number of monthly payments on a 5-year car loan? This seems like a common sense question. They're asking for monthly payments, so it's like you're going to buy a car and your loan is for 5 years and you have monthly payments. So how many payments do you make? Well, if you have monthly payments, that's 12 payments per year. And the car loan was 5 years, so it seems like pretty simple. You have to make 60 payments. So that wasn't very hard. And this next one is almost sort of common sense. In general, the longer the term of the loan, and you have an option. The answer is either higher or lower. The longer the term of the loan, the higher or lower the total interest paid on the loan. Well, normally, the goal is the sooner you pay it off, the less you pay in interest. So I would think the longer the loan, the higher your interest is. And that is the correct answer. So those are just more common sense. And 14, actually, I will talk about 14 just briefly. This is a problem talking about the definition of a function of an equation, because 14 says, determine whether the equation defines y as a function of x. Basically, they're asking the question, is this an equation? In case you don't know in math, for an equation to be a function, it has to meet some special criteria. And with equations, it can be a little tricky. Sometimes with graphs and other things, it's a little easier. Equations can be a little tricky. Here's one way to think about it. Here's a little test. If somehow one value of x, one number for x, if it can somehow produce two values for y, if somehow one value of x associated with two values of y, not a function. This can be sort of confusing. Let's just look at this example. Say I do a simple old-fashioned XY chart. Here's what I want to show you. What if I set y equal to 3? In this equation, what would x end up being? Well, 3 squared is 9, so x is 9. So in this case, when x is 9, y is 3. However, what if I set y equal to negative 3? Then from this equation, what is x going to be? Well, negative 3 squared is 9. So here's a case where one value for x, the same value, the number 9, can equal both 3 and negative 3. And by definition, that is not a function. All right, I'm not going to talk about that a lot more. It's a little bit esoteric, and function definitions are a little bit strange sometimes. However, let's do this one more problem, and then we'll shut down this video. Now, this is one that some students struggle with, so let me take a few minutes. They're asking for the domain, and the domain is going to be got a function p of t. Square root of t minus 5 over 4t minus 24. Let's talk about domain. Once again, this is function notation. This doesn't mean P times T. This means I've got a function or an equation. If I wanted to, I could almost say, I could rewrite it like this. Basically, I've got an equation for P that equals this. Function notation just basically says, hey, here's the name of my equation, and here's the variable that's going to be in the equation. In this case, the domain has to do with the letter T. And here's the definition I like to give, and then I'll explain how it works. Here's actually what the domain really means for this function. The domain is all the possible values of T. So T is my variable. The domain says, if I look at this equation, if I look at this function, what numbers could I plug in for T and everything's okay? In other words, nothing bad happens. You plug in a number for T and you calculate this and you get some number. It might be messy, it might be a fraction, it might be big or small, it might be a negative number, but it's a number. That's what domain means, which is a little strange to think about. Sometimes what's almost easier is to think of the opposite. Instead of thinking of what numbers, in other words, can I plug in 1 for T, and then if I do the math here, or can I plug in 10 for T, and if I do the math, is everything okay? Domain says, what numbers is it okay for T to be? An easier way to think about it is, let's think about this statement. What numbers can T not be? In other words, instead of thinking, what numbers can T be, how about we do the opposite and we say, well, let's see, are there any numbers that are going to cause me a problem? Any numbers that T cannot be for some reason? Is it going to cause me to break some math rule, or something bad going to happen if T equals a certain number? And you know what? When I asked this question, there were only 2 possibilities. Only 2 things that can happen where I'm going to have a problem with numbers for T. And the first one is, T's my variable, so let me just write here, if I ever have an equation and I'm looking for the domain, if I ever have a variable in the denominator of a fraction, then that's a case where I'm going to have some numbers that are going to cause me a problem. And let me go ahead and write this out, and let me do this problem, and then as we do an example, I think it'll be clear to you. So the first thing I have to be concerned about, when I look at a function or equation, and I'm looking for the domain, if I see any variables in the denominator, that's like a red flag. I've got to think about that. And the second thing I have to think about, when I look at a function or an equation, do I have any variables under the square root? In other words, that's a square root sign. Does my equation or function have any numbers under the square root? These are the only 2 situations that I have to worry about. So here's what I do. I'm given this function. I'm asked to find the domain. I start, first thing I do is I'm going to assume, to start with, I'm going to assume the domain is all real numbers. To start with, I'm going to assume in this case the domain is all real numbers, meaning t can be anything. That's my starting point. T can be any number. It's not a problem. No issues. So this is where I start. And then what I'm going to do, though, is I'm going to check for my two special cases. And only two special cases, That's all I have to check for. Nothing else. Once I check those two things out, I'm done. So the first question is, ask myself, the first one we need to look at, variable under the square root sign. If my function has a variable under the square root sign, then I have to sort of change my domain. My domain is not going to be all real numbers anymore. It's going to change. And after I figure this out, then I have to look at the second thing. And then I also say, is there any variables in the denominator of a fraction? Because if that's true, then my domain is going to change again. So really, if you think about it, the domain is going to be all real numbers except if one or both these things occur. If I have variables under the square root sign, my domain is going to change. It's not going to be all real numbers anymore. Or if I have variables in the denominator of a fraction, my domain is going to change. It's not going to be all real numbers. So let's do this example. And actually, I'm going to, well, I might have room here. I might run out of room. So I'm going to assume to start with the domain, that's the sign for all real numbers. Everything's a domain. I check the first thing. Okay, in my function, do I have any variables under a square root sign? And lo and behold, I do. T minus 5. Now here's the thing to think about. Why am I worried about what's going on under the square root sign? Well, think about it. Think about taking a square root. What do we have to make sure we never have under a square root sign? Well, if you remember, you can never have a negative number under the square root. In other words, I can never have a situation where I have something like square root of negative 4, because it's impossible. That number does not exist. I cannot take the square root of a negative number. So for my problem, here's what I have. I have to make sure, I have to figure out what values for t, if I plug in numbers for t, do I end up with a negative number under the square root? It could happen. I cannot let it happen, but it's possible. So let's go find the numbers for t that would cause me to have a negative number under the square root, and then those numbers are not in my domain. They're not allowed. I can't let that happen. I have to avoid ever having negative numbers under the square root. So how do I figure out when I have a problem? When does that occur? What you do is you take whatever is under the square root, and what we're really saying is I've got to make sure that whatever is under the square root, I've got to make sure it's greater than or equal to 0, which basically means I've got to make sure that this is either 0 or a positive number. That's what I'm really saying. This is how I make sure that I end up with a positive number under the square root. And I simply solve this inequality. So you know what I'm saying now? I'm saying when I look at that variable t, t has to be greater than or equal to 5. What happens if t is not greater than or equal to 5, I'll end up with a negative number under the square root, which I can't have. So in a sense, the domain says, okay, what numbers can t be? I've now have some numbers that t cannot be. In a sense, I say my domain is now going to be all numbers greater than or equal to 5. Matter of fact, if I were to sort of graph it, so if I say 5 is right here, the graph of this would be, in a sense, what I'm saying is right now, this is my domain. Once again, the domain is all the possible numbers for t. And I'm saying because I've got this square root here, t has to be greater than or equal to 5. Because if I pick a value for t over here that's less than 5, when I put it into the function or the equation, I'm going to end up with a negative number under the square root, which I cannot have. So this is a way to be sure that I never have any negative numbers under the square root sign. So the first thing I just now have checked out is having a variable under the square root. So let me write my conclusion here, because now I have to check out the other situation. So basically, I've determined t has to be greater than or equal to 5, and if I graph it, if 5 is right here. So right now, as of right now, this is my domain. Let me write my function over here again. This is what we're trying to find the domain of. So now I've evaluated the effect of having this square root here, and I've said the effect is it causes my domain to be all numbers greater than or equal to 5. When I first started, I could have any number, but because of this square root, I'm limited to all numbers greater than or equal to 5. But I said there are two things you have to check when you're looking for a domain. You have to see whether you have a variable under a square root, but then you also have to check for a variable in the denominator of a fraction. And we also have that. Now, what's the big deal about having a variable in the denominator of a fraction? Whenever we have a fraction, what is the one thing we can never have when we have a fraction? What is it? If you remember, you can never can have 0 in the denominator. And by that I mean the number 0. In other words, I cannot have a fraction like that. You're never, ever, ever allowed to have 0 in the denominator of a fraction. Now, if I look at my function, let's look at my denominator. Since I got a variable here, and I'm thinking, well, t can be anything, right? Well, no, it better not be. If there's a value for t that I plug in here, and this whole thing ends up being 0, then I got a problem. So what I have to do, I have to figure out what number for t will cause this thing to be 0. And then I have to say t cannot be allowed to be that number. Or another way of saying it is that number is not in the domain. It is not allowed. So all you do is you take your denominator and you set it equal to 0. So I'm going to figure out what's the value of t that would cause my denominator to be 0, and then I know I have to avoid that number. So if I solve for t, turns out t is 6. You know what that really means? It really means t cannot equal 6. Because if I plug a 6 in here for t, you know what happens to my denominator? It equals 0, and I can't have a 0 in the denominator fraction. So what I figured out is, because of this variable in the denominator, t cannot equal 6. So what I say is, the number 6 is not in my domain. It's not allowed. So far, here's what's happened for this problem. I began by saying, let's assume the domain is all real numbers. Any number's okay. However, when I looked at the square root part of it, I decided, well, not everything's okay. Turns out all my numbers have to be, the domain has to be greater than or equal to 5. And then I go look at the denominator and I say, hey, we know what else is true? T cannot be 6. Look up here. If it was just up to the square root, this would be my domain. But it's not up just to the square root. I also have to take into account the denominator. So now I have to sort of make my domain. I have to combine these two facts together. So here's the domain from the square root part. And from the denominator, it says t cannot be 6. Well, look at 6 is right here. If it was up to the square root's fine with 6. It doesn't care. It's not going to be a problem. However, it is going to be a problem with the denominator. So what do we do? In a sense, to make it clear, how about I redraw this graph? So here's 5. Here's 6. So what's my domain? My domain starts at 5, but what happens? When it gets up to 6, I cannot have 6. 6 is not part of the domain. I stop at 6, and I put a parenthesis because I cannot include 6 in my domain. However, if you look up here, what about all these numbers in here, this part of the domain, everything greater than 6? That's part of my domain. So what I do is, so I draw another parenthesis at 6, and then I keep on going. So what this is really saying is, the domain equals, I'll put it in words, all numbers greater than or equal to 5 except for 6. So the domain is what numbers can t be? Turns out t can be all numbers greater than or equal to 5 with one exception. It can't be 6. It can be everything else, but it can't be 6. So how do I write this in set notation, which that's how they want the answer? In set notation, which is sort of goofy, it's this t such that t, what we do is we first write sort of the number line part, t greater than or equal to 5, but then you have to include the exception for 6. So then we write t, but t cannot equal 6. So this part of it says, my domain are all the values of t greater than or equal to 5, with the exception of t equal to 6. All right, so let me just say it one more time as a review. Whenever you're asked to find the domain of a function or an equation, the first thing you say to yourself is, I'm going to assume the domain is all real numbers. I'm going to assume t can be anything. And then I'm going to look for the two special cases. Do I have a variable under the square root, or do I have a variable in the denominator? And I might have both. In this example, I have both. I have both special cases. So now I have to say, okay, I've got some special cases. My domain is not going to be all real numbers. It's not going to be everything. I have to see how my domain gets changed. You do the square root part, and like we talked about it, you create this inequality and you graph it, and then you look at your denominator, set it equal to 0, figure out what t cannot be, and then you combine all that information and you end up with your domain. All right, hopefully that clears it up for a lot of you for the test.